Hello, welcome to the sixth lecture for the class 11th mathematics, where we are dealing with the chapter 4, complex numbers and quadratic equations. So, we are still continuing with algebra of complex numbers. So, we have seen addition or getting a sum or difference or product or quotient using complex numbers, two or three complex numbers. We saw how we can find the power of a complex number, any power of complex numbers, and also trying to we have done how to get the square root of negative real numbers. So in the last class we had started how we about how we can apply identities on algebraic identities on complex number also. So we had tried to see the the complex the identities in the form of say z1 plus z2 the whole square. Okay, writing it in the similar form as how we write a plus b the whole square. Okay, so in the similar form we had established that it was z1 square plus 2z1 z2 plus z2 square. Okay, so we had also seen how we can find the whole square of the difference of two complex numbers. We also found the identity using we had proven how how we get this identity when we are applying it on the complex numbers. We also saw a few examples where we solved using the identity. So now till now we have seen what happens when we square the expression, whether it's the addition of two complex numbers or the difference of two complex numbers. Now we will see uh, what is the we will try to prove these identities. Okay, so we will be proving these identities, and also we will be seeing some prove these, also solve examples. Okay, so you can understand like you will see how you can simplify these kind of expressions. Okay, when we use the identities themselves. See, with the properties that we have learned with the multiplication between two complex numbers, we can apply those rules also. But it's easier if we simplify them in terms of the identities. So let's take the first one. Okay, so the first identity, like for the cube root, sorry, for the cube, power of 3 identity. So if we have z1 plus z2 cube, okay, so we have to prove that this is equals to z1 cube plus 3 z1 squared z and plus 3 z1 z2 squared plus z2 cube. Okay, so we have to prove. So now we will take the LHS part. Okay, so we will write it as z1 z2 multiplied by z1 plus z2 and multiplied by z1 by z2. Okay, sorry, z2. So you write, you find it would be a product. Okay, when you multiply it like thrice already. Now, first we take this part and z1 plus z2, z1 plus z2, okay, and z1 plus z2, we keep it out. Now this is of the form, sorry, z1 plus z2 the whole squared. Okay, so you can, we have already seen this identity, or you can actually use the distributive law and separate it out and solve it individually, using the distributive law and the associative and the commutative law, sorry. But since we know this identity already, so this would be z1 squared plus 2z1 z2 plus z2 squared. Okay, so we know this, so we can directly simplify this. So this would be z1 squared plus 2z1 z2 plus z2 squared. Okay, and then multiply the first bracket with z1 plus z2. Now we will use the distributive law. Okay, distributive law, and then we will multiply z1 square with first the this entire bracket with first the first term of the second bracket, and then with the second term of the second bracket. So this one will be z1 into z1 square, so z1 cube, plus this will be twice z1 square. Okay, and z2. Now this one will be plus z2 squared z1. Okay, and now you have plus, and now you multiply the first bracket with the second term of the second bracket. So what you get is z1 squared z2 plus z2. So over here 2 z1 z2 squared, 2 z1 z2 squared plus, and this will become z2 cube, z2 cube. Okay. So now you can easily see that, now it by opening up the brackets and putting the, uh, similar terms together. So over here, since you have z1 squared here and z2, z1 squared z2, so this will become 3 z1 squared z2 plus over here 2 and 1, so 3. Now over here, since we can, you can use the commutative law where, z1, z2 is equals to z2, z1. So it's the same, they both are same in whichever form you write. So you can write this as z1, z2 squared, okay? And then lastly, z2 cube, okay? So you can see that this is the RHS part. And then you can say this is hence proof. Okay. Now let's say, let's take the second identity of cube itself. So z1, z2, the whole cube. And it should be, what we will be proving is that this is equal to z1 cube minus 3z1 squared z2 plus 3z1 z2 squared plus, minus z2 cube. Okay, so now taking the LHS part, you do the similar kind of simplification. Z2, z1 minus z2, z1 minus z2. Okay, so this again, the first two terms you can think of it of the form z2 z1 minus z2 squared. Sorry. And then this would be z1 squared minus 2 z1 z2 plus z2 squared. Okay, so similarly, you can write this in this form. So you have z1 squared minus 2 z1 z2 plus z2 squared. Okay, and you have z1 minus z2 in the second bracket. Now again, similarly, you multiply the entire first bracket terms with the first with first with the first term of the second bracket, and then with the second term of the second bracket. So what you get is z1 cube minus 2 z1 squared z2 plus z2 squared z1. Okay, now you have the negative sign over here. So z2, so you have z1 squared z2. Okay. Then since we have already kept the minus sign out, so we will just directly multiply, okay, without changing the sign right now. So you have 2 z1 z2 squared, and then you have plus z2 cube. Okay. Now you take out the brackets and write all the similar terms together. So you have 2 minus 2 z1 square z2. Okay, so over here you have the same term over here. So this will be minus 3 z1 squared z2, and then you have z2 squared z1. Okay, and over here you have minus 2 z1 z2 squared, and if you multiply the minus sign, this becomes plus. And this again, because of the commutative law, it is similar to z1 z2 squared. So this is 3 z1 z2 squared. Okay, and then negative sign again comes here, and this will be z2 cube. Okay, and then this is equal to the RHS, and then we can write hence proved. Okay, let's take examples, and we'll see, using both the identities, what we can get. Okay, so question, suppose you are given Z1 is equals to 4 plus I, and your Z2 is equals to 3 plus 2I. Okay, so suppose you have to solve for Z1 plus Z2 cube. Okay, so if you substitute for the given values, we have 4 plus I plus 3 plus 2I, the whole cube. Okay, so now since we already know the identity, that Z1 plus Z2 the whole cube is equals to Z1 cube plus 3Z1 squared Z2 plus 3Z1 Z2 squared plus Z2 cubed. Okay, so this is the identity that we will use. So in that, or in those terms, what we will get is 4 plus I cube plus 3Z1, oh sorry. So 3 to keep out, and then you have Z1 squared, so 4 plus I squared, and then 3 plus 2I, and then you have 3Z1 Z2 squared, so you will get it as 3Z1 then Z2 squared would be 3 plus 2I squared. Okay, and then you have the last term, that is 3 plus 2I cube. Okay, so now we have expanded it. We have written it in the form of the proven identity. Now we will solve for the individual terms. Now this, 4 plus I cube or 3 plus 2I cube, or even for that matter, 4 plus I square. So these you can, expand in the general, identity form. Okay, so by a plus b whole cube or a plus b the whole square. Okay, so similarly, this would be so 4 cube. So you have 64 plus now you have 3a squared b. Okay, so in that case, you will have 48i, and then you have plus 12I squared, and you will have I cube. Okay, so this is the first term, expansion of 4 plus I the whole cube. Then you have plus, keep 3 outside for now, and expand 4 plus I the whole square. So that will be 16 plus 8I plus I squared. Okay, and you write 3 plus 2I again, and then you expand the third term. So you have 3, keep 4 plus I out, expand 3 plus 2I squared. So that gives you 9 plus 12I plus 4I squared. Okay, and now the last term, so that is the whole cube of 3 plus 2I. So you will have 27 plus 36 I, and then plus 36 I squared, and you will have 8i cube. Okay, you have 8i cube over here. Okay, so now we have to remember that I squared is equals to minus 1. Okay, and I cube is equals to minus I. Okay, so these are some of the general, powers of I that we know, and we had already proven it in previous classes. So we will substitute for those wherever we have got it. Okay, so actually this would be 12i squared. Okay, so let's substitute for this, and also we will multiply these terms together and also these terms together. So you have 64 plus 48i. This remains. Now this is I squared, so you have minus 1, so this becomes minus 12. And I cube is, it will be minus 1. Yeah. So this will be not minus 1, this will be minus I. Okay. Plus, now you keep 3 out and you multiply 3 plus 2i with 16 plus 8i plus I squared. So you will get 48, okay, plus 24 I plus 3 I squared. Now you can, directly substitute for I squared here, so you can reduce the number of steps over here. So this will become minus 3. Okay. Oh, sorry. I think I made a mistake over here. So actually, we will first multiply 3 with the first or the larger, bracketed term. So it gets easier for us to multiply later on. Okay, so now we will take out 3 from here since we have already multiplied it. And then you have 3 plus 2i, and then you have plus, you multiply 3 with the big, like the larger, term bracket over here. Then you get 27 plus 36i. And over here you will have 3 into 4, 12, and you have I squared. So you substitute I squared is equals to minus 1 directly. So you get minus 12, and this is multiplied by 4 plus I. And the last term that you have is 27 plus 36i. Over here, this becomes minus 36, and this would be minus 8i. Okay, so now we got this. Now write down all the other terms again. 48i minus 12 minus I. Yes, now you multiply this term with this bracket term. So what you get is 144 plus 72i minus 9 plus 96i minus 48 minus 6i. Okay, so this is a very long form, long solution that you'll be getting. And then you multiply 4 plus I with this entire term. So you have 108 and 108 plus 144 minus 144 I. Okay, so you will have 144 I. 144 I. Then you have minus 9. Sorry. This is not minus 9. It's 144I minus 48 plus 27I minus 36. minus 36 as in, you will get 36I into I. So you get 36I squared. So you automatically substitute for I squared over here. Okay. And the last one is minus 12I. Okay. And then you write the last one together. 36I minus 36 plus 8I. Okay. So this is the, how we are getting. Now I will just write the uh, term altogether. Okay. So if we take all the, real components to one side, okay, now since all the brackets, all the powers have been solved for, and all the multiplication of two, brackets of, complex numbers have been solved for. Now we can separate out the real terms and the imaginary terms, the coefficients of the imaginary part, and then we can get the final answer in the form of a plus ib. Okay, so for the real terms, you have 64 minus 12 plus 144 minus 9 minus 48 plus 108 minus 48 minus 36. Then you have 27 and minus 36 plus 27 minus 36. Okay, so this is all the these are all the real numbers, the real parts, and then you have I, and you have 47 plus 72 plus 26 minus 6 plus 144 plus 27 minus 12 plus 28. Okay, so some terms have already been, reduced to, so it gets easier. Okay, so now let's just solve. Okay, so 64 minus 1, this actually becomes your 154. Okay, and the I term becomes 47 plus 72 plus 96, sorry, 47 plus 72 plus 96, sorry, minus 6, and 44 plus 27. Okay, so this becomes 396 pi. Okay, okay. So this is what you get. Now you can obviously take out the highest common factor. You can solve it further. So, but this is how you can, solve for such identities and get it in the form of the a plus ib. And if we take the, now of the form of, if we have to find what is z1 minus z2 the whole cube, and suppose your z1 is, we take different numbers now. So you have 3 plus 2i, and z2 is equals to 1 plus 5i. Okay, so you directly substitute for the values of z1 and z2. 3 plus 2i, the whole cube, sorry, for the whole cube. Yeah, yeah, minus 1 plus 5i, the whole thing, the cube root. Okay, so now let's expand this. If like I will just write the identity that we will be using. Cube is equals to z1 cube minus 3 z1 squared z2 plus 3 z2 z1 squared minus z2 cube. Okay, so this is the identity that we will be using. Now let's say 3 plus 2i cube, okay, minus 3 z1 squared, so 3 plus 2i squared, okay, and then we have plus 3, sorry, missed term over here. Okay. So z1 squared z2. So z2 is 1 plus 5i. And then you have plus 3, 3 plus 2i, 1 plus 5i squared, okay, of this form. And then you have minus 1 plus 5i cube. Okay, so this is what we get. Let's wait a minute. Yeah. So now we expand these or the power identities that we have. So 3 plus 2i cube. Okay, so this we had solved before, so we can write it. 27 plus 36 minus 7. I think there's a mistake. E squared. Just hold on a minute. I think I'll have to make some changes in the previous slide because I think I have made some substitution errors. Sorry. Mm, just wait a minute. I think I made some substitution errors for the cube formulas over here. So I'll just cross check and I'll and do it again. Okay. Probably in this one. Okay. So you have 3 cubes, so that is 27. Then you have 3 a squared b. So that would be 3 into 9 into 2i. So that becomes 27 into 2. So this is should be actually 54i. Okay. And then you get 3a b squared. Okay, so that would be 3 into a into b squared would be 4i squared. Okay, so that becomes 9 into 4, so that is 36. And this will be I squared. So this is fine. And then you have 8 pi cube. Okay. So this was where I think we made a mistake. So now if the rest of it is hopefully correct, then we just quickly substitute and see 48i minus 12 minus I, okay, and plus 3. And what did we get for this? 3 into 16. Okay. So you have 48 plus 24i minus 3 plus 2i. Okay, and then you have 20. Sorry, there will be a plus sign here. So you have 27 plus 56i. 12 plus 1 is really minus 12. Okay, and 4 plus I. And here 27 plus 50 plus I minus 36. And you have minus 8i. Okay, so let's quickly, kind of substitute or take on the we get as 64 plus 48i minus 12 minus I plus 48 plus 24i minus, sorry, we have to multiply this. Okay, so now you multiply 3 plus 2i with the entire bracket over here. So that gives you 144 plus 72i minus 9. Okay, and you have plus 96i minus 48 minus 6i. Okay, and then we have plus 108 is 144i plus 7, sorry, plus 50. Okay, minus 48 plus 27i minus 36 minus 12i, and then you write the last entire term. Okay, then 54i plus 36 minus 8i. Okay, so if we quickly, just solve all the real parts, take all the real parts together. I'll just, kind of type the answer over here for, ease. Okay, so you have 64 plus, sorry, not plus, minus 12, okay, plus 144. For taking all the real ones. Okay, so let's just underline the real ones so it's easier for us to, kind of find it when we are trying to calculate the final one. 38 minus 36, 27, and minus 36. Okay, so plus 144 minus 9, minus 48 plus 108 minus 48 and minus 36 plus 27 minus 36. Okay, so you get 154 as we had got before. You take plus outside. So now you have all the i's. Okay, so i's, we take all the imaginary units. Okay, so you have 48 minus 1. Okay, I over here. Then you have plus 72 and you have plus 96 and then you have minus 6. Then you have plus 144, okay, plus 27, and then you have minus 12, and you have plus 54, and then you have minus 8. Okay, the last one is minus 8. So now you get 414i. Okay, so this is the correct solution for this. So since we realized that there was a issue in the substitution, so hence it is very important. So when you are expanding the brackets or writing the full form or full forms of the identities, it is important to take care, and it's better if you do all these steps step wise when you are solving it during your exam, so you don't make such mistakes. So let's continue with this. Okay, so let's expand 3 plus 2y. So again, if you remember, so this would be the second term will be 3a squared b. Okay, so 3 into a squared, that is 9. 3 into 9, 27, 27 into 2, so this will be 54. Okay, 27 into 2, 54 I. Okay, and then you have plus 36 I squared. Okay, since now you have 3ab squared. Okay, so 3 into 3, 9, 9 into 4, so 36, and I squared. And then you have plus 8i cubed. Okay, and then you have minus. Now we have a minus sign here. Expand this identity. So you have 9 and 2ab. So 6 into 3, yeah, 6 into 2, so you have 12. 12i plus 4i squared. Okay, and then 1 plus 5i, and then you have the next one. So 3 plus 2i, expand 1 plus 5i, so you have 1, 2ab, so this is 10i, and 25i squared, so this is uh, plus 25i squared. Okay, and the last one that we have 1 plus 5i cube. Okay, so 1 cube plus you have 3a squared b. So 3 into 5i is what we have, 3 into 5i, so it is 15i. Okay, and then you have 3ab squared. So 3 into 25. So you get that as so that is 75. Okay, and since this is b squared, we will have I squared over here. Okay, sorry, one more term comes here. Yeah. And then lastly, you have 125i cube. Okay, so substitute for the negatives and try to simplify and get it. 7 plus 54i. Okay, and this becomes minus 36. This becomes minus 8i. Minus, you can multiply the first bracket with 3. So you have 27 plus 36i. And you have say plus. Now, if you directly write it as by substituting I square is equals to minus 1, so this will be minus 12. Okay, and 1 plus 5 5, 1 plus, and then you have 3 plus 2i. You multiply the bigger bracket with 3, so what you get is 3 plus 30i. Okay, and plus 75i square. And this is minus 1 plus 15i. And you can directly write this as minus 75, since we have I squared over here. Okay, and then you can go with plus 75. So it will be minus 75. Okay, and we have minus 125i. Okay, so this is what you get. Then again simplify further. 27 plus 54i minus 36 minus 8i. Then you have minus 27. Or then over here, since you multiply 1 plus 5i with this larger bracket term, so you get 27 plus 36i minus 12, then 5 with 27. So that is okay, so plus 135, and then you directly substitute for I square when you're multiplying 5i and 36. So that is 180 and minus 60i. Okay. And then the next bracket term would be 9 plus 90i minus 225 minus 6i minus 60 minus 155. And the last bracket, you can keep it. 1 plus 15i minus 75 minus 125i. Okay. Now, if we quickly just solve for the real parts. So you have, I'll just mark it with red as I go. So real parts are 27, and then you have minus 36. Okay, then you have minus 27. Okay, so now suppose we are, taking the negative signs inside the brackets now. So, and then you have plus 12. Okay, so minus minus over here, this becomes plus 12. Then you have minus 135. Okay, and you have minus 180. Sorry, this actually there is an I over here, so this becomes an imaginary part. It's a written by mistake. Yeah, 5I into 27. Okay, so we will get the next one. So this would be plus 180. Okay, so you have minus 12, and then you have plus 180. Okay, and then you have plus 9 and minus 225 minus 60. Okay, minus 60, and then you have minus 1, and you have the last one, that is minus 75. Okay, so this we get as, just cross check once if all the terms have been taken properly. We have 27 minus 36 minus 27 plus 12 plus 12, then plus 180 plus 9, and you have minus 225 and minus 60, then you have minus 1. Yeah, so this will be plus 75. Okay, so the real part gives us minus 46. Okay, now let's see what would be the imaginary part. Okay, so now let's take all the imaginary terms. So you have 54. Okay, then 54I. So we are keeping I outside. Okay, so I has already been taken outside. So only the coefficients we will, solve. So you have 54 minus 8. Okay, then you have minus 36. Then you have plus 135. And then you have, sorry, this not be plus. This will be negative because we have the negative sign outside. Okay, so minus 135. Then you have minus 60 here, so this becomes plus 60. And then you have plus 90. And then you have negative 6, sorry, minus 6. And you have minus 150. And then lastly, you have minus 15. And you have plus 125. Okay, so that gives us actually minus 21. Okay, so what we get is, we take the negative sign outside, so you get 46 plus 21I. Okay, so this is your final answer for when we solve z1 minus z2 cube using these two values. Okay, so yeah, obviously that took a little slightly longer than expected. Okay, so now we saw a few examples of when we take the whole power of either sum of two complex numbers, or difference of two complex numbers, but using the identities to solve them. Now let's solve a few other examples. Okay, so which have been kind of asked previously in your different kinds of entrance exams, or for larger kind of exams that you have. So the first question is, okay, so now we'll see that sometimes in the trigonometric terms, okay, or formulae can also be used in the form of complex numbers. Okay, so suppose you can have a complex number, okay, where cos of say theta is the real part, and if you have I sine theta, this becomes your imaginary part of the complex number. Okay, so you can have complex numbers in the form of where you have to take the cos of an angle or a sine of an angle. Okay, and usually this can also be expressed in exponential form as this. Okay, so e raised to I theta. Okay, so these are something that you can remember. for now, when we solve some examples where we will require, these kind of values. So let's see. So over here, we are given that cos alpha plus cos beta plus cos gamma is equals to sin alpha plus sin beta plus sin gamma, and that both these terms are actually equal to 0. If this is a condition that is given, we want to find the value of cos 3 alpha plus cos 3 beta plus cos 3 gamma. Okay, so now we will, find the solution as let A is equals to cos alpha plus I sin alpha. Okay, and then you have B is equals to cos beta plus I sin beta, and C is equals to cos gamma plus I sin gamma. Okay, so we are considering, three terms A, B, C, and they are written in the form of, cos, in the form of cos and sine of alpha, beta, gamma. So now, since we have these conditions already, okay, so what would that mean is that if you kind of add all the three, terms, the complex numbers, so what you get is cos alpha plus I sin alpha. Okay, then you have cos plus cos beta plus I sin beta plus cos gamma plus I sin gamma. Okay, so if you separate out cos alpha plus cos beta plus cos gamma plus I sin alpha plus sin beta plus sin gamma. Okay, and since we know that this equals to 0 and as well as this equals to 0, so therefore we can say that A plus B plus C is equals to 0. Okay, now to get in the form of 3 alpha, 3 beta and 3 gamma. Okay, now as we have seen, E I theta. Okay, so E raised to I theta is equals to cos theta plus I sin theta. Okay, so now if you cube this, okay, if you put any kind of if you take the power of this entire expression, this can actually be it corresponds to E I theta raised to k. Okay, so that actually becomes E raised to I k theta. Now you can see that this can now be written in the terms of cos k theta plus I sin k theta. Okay, so now if you're given cos 3 alpha and 3 beta, so you can see that if the coefficient or the number that you're multiplying with theta is 3 over here, then that means the power actually becomes 3. So therefore, if you have I theta, raised to q, so you have E I 3 theta, and that is equal to cos 3 theta plus I sin 3 theta. Okay, so now we will try to get these, kind of terms in form of this. So if we have to, and this then equals to, then you can write this as so cos theta plus I sin theta the whole cube. Okay, so this is what we have proven. So then we can write that, then if we cube the entire, the summation. Okay, so A plus B plus C the whole cube. Okay, so we will try to see that, what will we get. Okay, so what will this be? Now, as we have seen the, cube identity that we solved before, So let's try to find what would be the the identity associated with a plus b plus c the whole cube. Okay, so now this is not a part of the solution, but this is to simplify your understanding of what we will be finally what form of this identity we can use when we are trying to solve. Okay, to get the answer to this. Okay, so let's take that. Okay. So you can, simplify it in terms of a plus b plus c multiplied by a plus b plus c and a plus b plus c. Okay, so let's solve this. We have a squared plus ab plus ac. Okay, and then you have plus ab plus b squared plus bc. Okay, and then you have ac plus bc plus c squared multiplied by a plus b plus b c, sorry, and then you again multiply this, so you have a cube, okay, you have plus a squared b plus a squared c plus a squared b plus a b squared plus a b c plus a squared c plus a b c plus a c squared. Okay, now you take the b parts. So you have b a squared plus a b squared. You multiply b with this entire first bracket. Okay, so you have again a b c plus a b squared plus b cube plus b squared c plus a b c. Okay, and then you have plus b squared c plus c squared b. Okay, and then you actually get a squared c plus abc plus ac squared plus abc again plus b squared c bc squared plus ac squared plus bc squared plus aq. Okay, so now if you take aq plus bq plus aq, okay, outside. So if you actually simplify, and try to, take all the different, you can club a square, a square c, a square. Okay, so if we start with a squared b first, okay, so you have one a squared b, okay, a squared b, a squared b, a squared b, okay, and a squared b again, okay. So actually, if you club all of them together, so what you actually get is 3a plus b, b plus c, then a plus c. Okay, so if you actually simplify, this is what we get. Now, if we have, this is the final form of the, this is the final identity that we can use for this sum, for, solving this sum. So now, since we know that a plus b plus c is equal to 0. Okay, so this we have already proven. So then you can write in the terms that, a plus b is equal to minus c, okay, b plus c is equal to minus a, and a plus c is equal to minus b. Okay, so therefore you can write this in the terms that a plus b plus c the whole cube actually becomes a cube plus b cube plus c cube. Okay, and then that is you substitute for these. Okay, so you have plus 3, then you have minus c minus a, and you have minus b, and then you can write a cube plus b cube plus c cube, and this will be minus 3abc. Now, since we already know a plus b plus c is equals to 0, therefore a cube plus b cube plus C cube is equals to 3ABC. Okay, so now you substitute for A, B, and C as we have already, already considered for, the different terms. So you have A cube, so that is cos alpha plus I sin alpha the whole cube, plus you have cos of beta plus I sin beta, okay, the whole cube, plus cos of gamma plus I sin gamma the whole cube, and you have 3 into cos alpha plus I sin alpha multiplied by cos beta, okay, cos beta plus I sin beta, and then you have cos gamma plus I sin gamma. Okay, so this is what we have. Now, if since you remember that E k theta is equals to cos of k theta plus I sin k theta. Okay, so similarly, and that would equal to cos theta plus I sin theta raised to k. Okay, so you can substitute, the multiplicative factor for all the theta for these terms. So what you get is cos of 3 alpha plus I sin 3 alpha plus cos 3 beta plus I sin 3 beta plus cos of 3 gamma plus I sin 3 gamma. Okay. Now, for this again, okay, so there is another, formula. If in the similar sense that, we can write this, if you have alpha plus e raised to I beta plus e raised to I, you know, gamma, this actually can be written in the form of alpha plus beta plus gamma. Okay, you can write it in that form also. So you can change, and this the 3, if you say, if you have actually, sorry, I forgot. So this you can write in this form. Okay, so now if you have, k, k factor in front of the angles. Okay, so suppose you have a this I k gamma, you can write this as 3 e raised to I alpha plus beta plus gamma. Now, if you write the exponential in the trigonometric terms, you can write this as 3. Okay, so 3 cos of alpha plus beta plus gamma, and you will have plus I sine of alpha plus beta plus gamma. Okay, so if we know this also, okay, so I will just, kind of make a star sign over here. So, this is the, condition that we are using. And this is the second condition that we are using. Okay, so then for this, you can, refer to the star condition. And now because of the asterisk mark condition, we can simplify this part as 3 cos of, okay, so 3 cos of alpha plus beta plus gamma plus 3 I sine of alpha plus beta plus gamma. Okay, so now in the question we've been asked what is the value of cos 3 alpha plus cos 3 beta plus cos 3 gamma. Okay, now over here you can see that cos alpha, cos beta, and cos gamma are actually the real part. Okay, so they are asking the to compute the real part. Okay, so the real part of LHS is actually cos 3 alpha plus cos 3 beta plus cos 3 gamma, okay, will be equal to the real RHS. Okay, real RHS. So that is actually equal to this. Okay, so that is 3 cos alpha plus beta plus gamma. Okay, similarly, you can have, like, for the imaginary part, if you are asked, to equate the imaginary parts also. So therefore, you can write that as that sine, the value of sine, sorry, this would be alpha. Yeah. So sine 3 alpha plus sine 3 beta plus sine 3 gamma is equals to 3 sine alpha plus beta plus gamma. Okay, so you can see how, uh, we used the identity over here. Okay, so which we have proven over here. You can actually simplify, break up all the uh, different terms over here, and you can club together, and you will see that it actually, you get it in this form. So you can solve it on your own, and you can see, and we have used that over here along with some general, trigonometric trigonometric expressions. Okay, so like where we are using the exponential form, and we are writing the imaginary kind of, we are accommodating or including the imaginary part also. And we can see that there are different kind of complex numbers which have your trigonometric functions as well as, an imaginary unit. So this is one example where you can where you can solve and simplify, with respect to complex numbers. So today we will stop here, and we will continue in the next class. So thank you so much. Hopefully this has helped you.